All right, welcome back, everyone. For the main seminar today, we have Shanshan Hua from the University of Minster as well, and she will be talking about Cartan subalgebras of self-similar graph C-star algebras. Go ahead.
Thanks, Ben. Also, thanks very much for inviting me here to give a talk. So today I'm going to talk about, as the title suggests, we'll be looking at a quite large class of C-star algebras, which are coming from self-similar graphs. And we're trying to, not being so ambitious, try to classify the Cartans inside of this class of C-star algebra, but rather try to just show existence of Cartan subalgebras, at least in a large class of, or like a subclass of these things. So the talk will be briefly divided into three parts. The first part will totally on the dynamical side. I will try to tell you what a self-similar graph is. So it's basically a self-similar action of a group on a directed graph. And the second part of the talk, we're going to see like how to encode this dynamical data into a C-star algebra in various different ways. But the actual important underlying model for these C-star algebras are really the underlying groupoid. So I'll probably pay a little bit more attention onto the underlying groupoid. And then for the third part, we'll try to see the strategies of finding Cartan subalgebras in the C-star algebras from the original groupoid model. So that's the basic plan of the talk. Okay, so let's start with these self-similar graphs. So part of my input data is going to be E. So this is a directed graph. I will just denote by E naught the set of vertices, and E1 the set of edges. And similarly, E star, the set of finite paths, and also E infinity, the set of infinite paths. So my infinite paths always goes like this. So kind of extend infinitely on that side. Right. And some assumptions that I want to put on my graph to make it slightly nicer. One of them is that I want both E naught and E1. So they only have like finitely many vertices and edges. And secondly, we will assume that our E is source-free. So for every vertex, you always have some edge going into it. So this is basically try to make sure that we have enough infinite paths to play around. So one could also work outside of setting, but require a little bit more technicalities to deal with the situation. So just for this talk, we wanted to be able to assume it's source-free, and also you have some level of finiteness. So later on, when we associate a C-star algebra to it, the C-star algebra is guaranteed to be unital. Source-free. So you don't have any source, meaning that so if you look at the set of mu such that source of mu equal to some vertex phi is non-empty. So for every vertex, you can always find some. Range. Really. Yeah. So yeah, like if this is my finite path, then this will be called my source of the finite path, and this will be called my range of finite path. And I can concatenate two, let's say, edges, so mu1 and mu2, if the range of mu1 is the same, the source of the range of mu2 is the same as the source of mu1. So that's the notation that I'm going to use for the graph. Okay. And the second part of data is this group G, which throughout the talk will be assumed to be a discrete, countable group. And I will be talking about the groups acting on the graph. So what do I mean by that? So when I say an automorphism of the graph E, I mean it's a map from, so it's a bijection from E star to E star that preserves length, range, and source. Okay. Then I will say that G acts on E if there is a group homomorphism from G to the automorphism group. And to simplify the notation, so let's say this is phi, I'll just denote by G acting on some finite path mu. So this really means that I take the group element G, it indicates for me an automorphism of phi, and it will send mu to somewhere else. So this is my notation.
Sorry.
Yes.
So an alpha, is that the same thing as bijection of the vertices that is
Yeah. Like you can either define it on the level of finite paths, or you can just try to determine where the vertices are sent and where the like these edges are sent, and this will like completely determine the whole action. So now we're ready to look at this definition of self-similar graphs, which is introduced by Excel and Pardo. And so they introduced this definition, really try to recover a lot of like important C-star algebras that already exist in the literature at the time. So for instance, the Nekrashevich algebra coming from the study of self-similar groups, or this Katsura algebra, which Katsura used to realize some Kirchberg algebra. So this class of C-star algebra will be very, very broad, but let's start with the dynamical data that defines them. So if I have an action of G on E is self-similar if, well, so if you kind of imagine the most trivial action you can think of, you probably, so when G act on a concatenation of mu and nu, you probably wanted to say that, well, let's just let G act on mu and let G act on nu. So self-similar action is slightly more general than that. So the basic idea is that after you let G act on the first segment of your finite path, you will kind of allow a little bit twist of your group element. So kind of twist this group element to some other group element, but this rule is witnessed by something called a restriction map. So if there is a restriction map where it's a map that I take pair of group element and finite path, and it gives me another group element. So satisfying, well, first of all, this rule that indicates for you the self-similarity, and the rest axioms really tell you how to extend this to the whole action. So when you when you restrict to mu and nu, it will be the same as if you restrict to mu and then restrict to nu. And if you have two elements G and H multiplied together, this will be the same as G restrict to H times mu and then H restrict to mu. And lastly, if you restrict a group element to a vertex, you still get the group element. If you have the identity element of the group restrict to anything, it's still just the identity element. So really, if you think of these as axioms, this is a really important thing. And the rest bits of the thing is trying to make sure that you're actually defining an action of G on this finite graph. So once you have this self-similar action, there is an induced action of G on the infinite path space, a very natural one. So if you start with an infinite path X, so let's say X 0, 1, X 1, 2, and so on and so forth. So in order to tell you where this infinite path is sent, you could already imagine that. So let me pick a group element G. Well, the natural way that to follow this self-similarity is that, well, I use this element G to send x0, 1 to somewhere else. So send by G to, say, G times x0, 1. And when I do the second part of the action, I kind of need to twist this group element G a little bit by what I have traverses. So here, I will act by this element when restrict to x0, 1. So move this to somewhere. The acting element is changed, but acting on x 1, and so on and so forth. It's really a very naturally induced action of the group G on the infinite path space. Do we have any questions before proceed to next part? So now we'll be talking about these self-similar graph C-star algebras. So there are various parts of the data that you need to encode into C-star algebras. As you can see from this definition, you have the data from the finite directed graph E, and you have the data from G, and you also have the data from this self-similar actions. These are the data you want to encode. So maybe some of you might be familiar with how do you encode the data of a group into C-star algebra. You can take these unitary regular representations, and you can get the full C-star algebra or reduced group C-star algebra. So starting from a directed graph, you can take this Quinn-Squeeger class, which are like partial isometries associated to each edge and projections associated to each vertices. And you have some relation between them according to how the edges going in and out of the vertices. So when we're defining this self-similar graph C-star algebra, it's very similar to that. So I'll denote by OGE, the self-similar graph C-star algebra that I obtained. So this will be the universal C-star algebra of the generators. So first of all, the unitaries for each group element G, but I also want this to be a unitary representation, meaning that UGH is equal to UGUH. And secondly, I have these partial isometries. So as mu for each of the finite paths, that they form a Quinn-Squeeger family. Now, I'll briefly say what this means. So it means that this partial isometry is corresponding to vertices. So these are mutually orthogonal projections. These vertices are kind of like partition your Hilbert space into several parts. And so if you have two concatenate finite paths, mu and nu, then S mu nu is equal to S mu and S nu. And thirdly, So if you take your S mu, where source of mu is equal to V, you have the relation that S mu star S mu is equal to the S corresponding to this V. And lastly, if you look at the projection corresponding to a vertex, it's kind of the sum of range projections of the partial isometries with edges going into that particular vertex. So if you have a vertex V here and you have several edges going into it, then this SV, which is a projection, will be the sum of S mu star, which is the range projection of these S mu with range of mu V. So previously we have assumed that we only have finitely many vertices and finite edges. So this avoids the problem that you might have some infinite sum. So it's really well defined. Okay. So these are the generators that I will just pull into my C-star algebra. And I haven't indicated for you the relation they need to satisfy. Well, so they already have some relations to satisfy. Well, it's a unitary representation, it's a closed creature family. But moreover, I want this self-similarity condition to appear. So I wanted them to satisfy that if I have UG times S mu, so my G will move the finite path mu to somewhere else. So this is the same as SG act on mu and U G restrict to mu. So it really tells you that when you act by G on mu, you first of all change this finite path to somewhere else, and then your group element is getting twisted a little bit. Okay. So this is my universal C-star algebra that encodes the self-similarity of the action. Yes.
If we don't have a self-similar, it means that the reflection path is identity, then is able to definition of the graphs is
It's actually a very good observation, but not the identity. I think maybe you mean that so if G restrict to mu is G, or so in this case you'll get something like a cross product. This is actually going to be contained in the kind of class examples that are covered by this construction. So that's a very good observation. So examples. Well, first of all, as what you have suggested, if G restrict to mu is equal to G, for any G in G and mu in finite path, then the relation that we have above becomes UG as mu equal to SG dot mu UG. So if you move your UG to this side, you'll get UG as mu UG star is equal to SG dot mu. So really expecting that, so your the self-similar graph C-star algebra you get is really just, well, you take the graph C-star algebra and you have this action by G. Okay, so the second class of examples are these Nekrashevich algebras. Which are defined by Nekrashevich to study these self-similar groups. So the defining property of self-similar groups really means that the group kind of have the self-similar action on these finite words coming from finite alphabets. So the way of associating these self-similar graph C-star algebras to Nekrashevich algebras is really the following. So he has the initial data being the group and some finite set of alphabet that you construct these finite words from. So what you can do is that you take the graph who only have a single vertex and edges being the loops around this vertex, so being the set X. And then the self-similar graph C-star algebra constructed above will be the same as these Nekrashevich algebras. So the third class of example are the Katsura algebras. So the original way that these Katsura algebras are defined are by two n by n matrices where the entry of each of the matrices are just integers. So you can try to associate, well, positive integers. So you can try to associate one of the matrix to be the adjacency matrix of the graph and the second matrix encoding the self-similar action. And these examples are actually just covered by the self-similar graphs where you take the group to be just Z. And maybe it's worth mentioning that this class of Katsura algebras is extremely broad, that so these classes are contained here, and it already covers all UCT Kirchberg algebras. So these are simple, separable, unital, nuclear C-star algebras that are purely infinite that satisfy this universal coefficient theorem that Philip also mentioned in the talk. And it's probably worth mentioning that so this picture was helpful in Katsura's proof. That all set to the n actions on the Elliott invariant of these UCT Kirchberg algebras lift to actual actions. So this self-similar graph C-star algebra picture of Kirchberg algebras indeed help with some of the studies or the questions that people are interested in. Yes.
If your graph has a cycle, or let's say a loop at a vertex, doesn't that mean you can have like infinitely many finite paths?
Yeah. What do you mean by infinitely many? Yeah, you surely have many finite paths.
So I'm just like the sum in the condition 4 in the.
Sorry.
Yes.
Of a particular length. You're 100% right.
Right.
So for any natural number, and you have the length of this unit.
Okay.
Yes.
Okay. Thank you. Thanks.
Sorry, when I was writing that, I was really thinking of these mu being edges, but you're 100% right.
Right.
We need to kind
Gotcha.
of like fix the length of the
Gotcha. Okay.
paths.
Cool.
Okay, so now we will switch to the group point of view of these self-similar graph C-star algebras. And for those of you who might, can I just like start with like saying things about groupoid, or maybe we want like a really quick saying of what groupoid are briefly? The audience have them. Okay, then I'll probably just go relative directly to saying what the groupoid is like. But some notations maybe. So this groupoid will be, well, I currently don't assume anything on this. It's just a topological groupoid, maybe locally compact Hausdorff. And then by G naught, this I will mean the collection of source and ranges. So it's like collection of gamma gamma inverse or gamma inverse gamma, where gamma are elements from a groupoid. And by iso of G, I mean the collection of all those isotropy element. So these are the gamma in the groupoid, such that the source of gamma, let's just say that the source of gamma will be So gamma. So it just be this one. So this is the source of the gamma, and then this is the range of the gamma. And the isotropy are those groupoid elements that the source and the range are the same. Okay. So these will be important, as you have seen in Philip's talk, especially for the study of Cartans. So for instance, Philip has mentioned that if the groupoid is principal, meaning that your the unit space is the same as the isotropy of the groupoid, then the continuous functions on the unit space already give you a C-star diagonal. And if you're topologically principal, meaning that you have the unit space the same as the interior of the isotropy, then your continuous functions on the unit space of the groupoid will give you Cartan subalgebras. And I wanted to just mention that in the cases that we're interested in, the groupoid are usually not principal and not topologically principal. So it's indeed a new question to try to find Cartan subalgebras in this big class of self-similar graph C algebras. Okay. So I'm going to mention this groupoid for self-similar graphs. And for some of you who might already seen these graph groupoid before, you might be familiar with is that they're just like tail equivalence relations of infinite paths. And in the case of self-similar graph, it's very similar. You also have this tail equivalence relations, but the difference is that you kind of need to encode the dynamical data. So the group action and also the self-similar, so this restriction map. So the self-similar graph groupoid, which I'll denote as GGE. So the groupoid element are of the following form. So similarly as this tail equivalence relations in the graph groupoid, you kind of having this ux and ux. And the integer lag that reporting how many, or how long do you need to shift the finite path so that the eventual thing look exactly the same. But as what I have mentioned, we also want to encode the dynamical data. So here you will have g.x. And here I will have rather just say it's ... So some information that I don't want to explicitly say what they are, but I will briefly tell you what are actually contained here based on just the intuition. So instead of here, it's really encoding how G changes when traversing the infinite path X. So it's really like a dictionary. You start with G, and then when passing through the first edge of X, your G change to G restrict to 0, 1. And then when passing to the second edge, your G restrict to X to 0, 1, X 1, 2, and so on and so forth. So this part of the information is really like a bookkeeping of how the group element gradually changes over this infinite path. It's slightly more than that. I'm slightly lying here, but the actual algebraic details is not actually that relevant to this talk. So, right. Right. So in order to for this element to make sense, I kind of need to make sure that while the ending point of x00, which is going to be the source of nu, when I map that source of nu by G is going to be the source of mu, right? So this is the compatibility condition. So saying source of mu needs to be G acting on source of mu. And let me just briefly say how the source map, range map, and the multiplication for this groupoid is defined. Just to give you some intuition that this groupoid is probably not that far away from the past groupoid that probably you're more familiar with. So source of, let me call this groupoid element gamma. So source of gamma will just be mu x, the trivial data in this dot dot part, 0, and then mu x. And range of gamma is very similar. You just have mu g dot x, trivial dot dot data, 0, and mu g dot x. So similarly, if you try to multiply two groupoid elements, you need to make sure that this, the range of the groupoid element on the right is same as groupoid element on the left. And you just add up the integer part, but you need to do a little bit non-trivial thing on this dot part. That's how you do the groupoid element multiplication. Okay. And very similar to the graph groupoid, where you have these cylinder sets to give you a topology of the groupoid. Here we also have the topology that coming from these cylinder sets. So take the cylinder sets. So denote them by Z mu g nu. Where mu g nu will satisfy the compatibility condition there. So S of mu equal to G dot S of nu. So this set will be containing those groupoid elements that, well, you start with mu, and you just look at, you start with mu, and you look at what infinite paths that you have follow this nu. And you form elements of the form mu g dot x, the self-similar part, d mu minus d nu, and nu x, where x0, 0 is source of nu. So this will be our cylinder sets. So under the topology generated by these cylinder sets, this self-similar graph groupoid GGE will be a locally compact topological groupoid. And you might have noticed that when I write down the properties that this groupoid already have, I didn't mention Hausdorff because it will not automatically be Hausdorff. We need some extra dynamical conditions so that the groupoid that we work with are actually Hausdorff. And this condition is kind of like a freeness, but it's much weaker. So under this condition called pseudo-free, which means that if G fixes some finite path mu, well, freeness will just tell you that then this G has to be the trivial group element. But pseudo-freeness means that if G fixes the mu and G restrict to mu is the identity of the group, then this implies for you that G is the identity element. So under this condition, this GGE will be Hausdorff. And it's a very nice topology in the sense that so these cylinder sets Z mu G nu form a basis. Okay. Then furthermore, for the rest of the talk, we would hope to work with amenable groupoid or nuclear C star algebras. So under the condition that G is amenable, then GGE is amenable, and the reduced groupoid C star algebra coming from GGE will be the same as the full groupoid C star algebra coming from GGE, which will recover the self-similar graph C star algebra. So really, the amenability is used here, and pseudo-freeness is used to have this isomorphism, because the way they prove it is not directly proving that these two C star algebras are the same, but rather through some other tight groupoid of the semi-group action. And they kind of only coincide under the pseudo-freeness. So here is where amenability comes in, and here is where pseudo-freeness comes in. Yes. Yes, étal. So étal, you already have. So right. May I know how should I erase this?
There's a
Okay, so it's the German.
yeah. Well, you can also just use the
Sponge.
the blue.
Oh, the white, yeah. Yeah, I'll probably just directly use this.
Yeah.
Yeah. A little bit.
It's amenability of the
Yes.
graph report is equivalent to amenability of the G, or is it for like the action somehow? Or?
I think this is just a sufficient condition. I'm not totally sure whether this would be necessary, but I would think it shouldn't, because in the cross product case, at least you're more looking for things like the amenability of the action.
Yeah, so that's what I was saying. Amenability of the action.
Yeah. But I also wouldn't be super surprised if
It's not.
Yeah, it's not obvious for me if So now we're going to the Cartan subalgebras of these self-similar graph C star algebras. And I think Philip has introduced to you the notions of the Cartan and why people might be interested in understanding these substructures and its correspondence to the groupoid, and like what happens in special cases if you do have principality and topologically principal. And I think it might be worthwhile to mention a very easy example of not topologically principal, not principal groupoid that kind of just naturally arises when you already start to work with graph C star algebras. I mean, the easiest example that one might think of is this. So you have like a directed graph. You don't even need to define any group or the self-similar action. You have one vertex and one edge, so it's a loop. And then the corresponding C-star algebra will be C of t, because if you write out the Quinn-Squeeger family, you can see that you're basically just defining the C-star algebra generated by a unitary, right? And if you look at this path groupoid, so the unit space of the path groupoid can be identified with the set of infinite paths. And in this case, you only have one infinite path. So the unit space in this case would just be a singleton. But if you look at the isotropy of your path groupoid, so these are tail equivalence relations, but you know that you can shift by any length and shift the other side by any length, and then the eventual thing will be the same because you only have one infinite path. So the isotropy of the groupoid is actually set. So it's already a very easy example that once you step into the world of either graph C-star algebra or self-similar graph C-star algebra, you already have examples that your groupoid is not even topologically principal. And in this case, what is giving you the Cartan is really just the whole thing, but not the one coming from the unit space. So hopefully that's slightly more convincing that when we're considering Cartans of this self-similar graph C-star algebras, we're considering something that hasn't been already covered in the previous literature. And more precisely, or even more importantly, the kind of question that we're looking at is really, so if my C-star algebra A is a reduced groupoid C-star algebra of some groupoid G, in this case, we'll just have self-similar graph groupoid. Can I identify a subgroupoid H and G such that the reduced groupoid of H, the subalgebra in the reduced groupoid C-star algebra in G, is a Cartan subalgebra. Well, so first observation would be the following. So if I could ever having a Cartan subalgebra in here, and that comes from a subgroupoid, then H has to be a open abelian subgroupoid in the interior of the isotropy, or just the isotropy, they're equivalent. So openness is really needed because you get a subalgebra, and abelian together with it is in the interior of the isotropy will give you that this subalgebra you get is abelian. So this is really due to the reason that if you have some element that is not inside of the isotropy, you can get this gamma inverse and gamma inverse gamma. The source and range will not be the same. So that's already the no abelianness appearing. So in conclusion, the answer to this question will be to find an abelian open subgroupoid in the interior of the isotropy that satisfies some further conditions so that you actually get a Cartan. So the first case of our interest is where, so is in this case, where I'll just call it like the genuine actions. So I have the cross product of the graph C-star algebra with G. And in this case, the self-similar graph groupoid will just be isomorphic to, you take the graph groupoid, and then you kind of cross product on the group G. And there's a natural action induced from your original action. And even in this case, we kind of didn't find much result in the previous literature, even covering the case for like G being Z. So first of all, the lemma. If G is abelian, then it turns out that the interior of the isotropy of the groupoid is abelian. So if I ever wanted to find a Cartan coming from these subgroupoids, then the interior of the isotropy itself is the only option here. And then we can invoke this result by Brown, Nagy, Resnikov, and Sims, William, 2016, where they show that so if my groupoid satisfies all of the nice conditions that I mentioned there, if the interior of the groupoid is abelian enclosed, then this C-star algebra of the interior of the isotropy gives a Cartan. Okay, so as you can see, in order to get Cartan in these cross products, really what we need to do is really the closeness. And this closeness is actually necessary because in order to get this conditional expectation, you will need the closeness of the groupoid. It's really an if and only if. But like in our case, because really we're trying, yeah, sure. So the first theorem, let this self-similar graph be a genuine action. It just means that the G restricted to mu is equal to G for any G and any mu. The following are equivalent. Well, first of all, the interior, be a genuine action and G abelian. The interior of the isotropy is a Cartan subalgebra. If and only if, so we're basically characterizing the closeness of the interior of the isotropy. So it's some condition that is expressed in terms of the dynamical behavior of the system, but I probably wouldn't like to indicate the actual definitions. So for any x being the infinite path and any group element G, x is either G generic or G rare. So there are conditions that you can verify in the examples that you have, and you can really consider them as direct translations of what is needed for closeness. Okay. So this is the first theorem that we obtained in the case of cross product. So secondly, in the more general setting. So in the more general case, things become increasingly complicated. And the complication come from two things. Well, the first thing being that we don't have a complete understanding of what the interior of the isotropy looks like. And the second is that even we understand how the interior of the isotropy looks like, this choice of subgroupoid will never be canonical. So you can always like pick out a little bit of the subgroupoid, add in a little bit more, try to make it a maximal abelian, but these choices are just not canonical at all. So what we did successfully in the first stage is that we're able to completely understand the interior of the isotropy of these self-similar groupoid. And for the second step, we identified a special subgroupoid. Under some conditions, they will indeed give you a Cartan. Okay, so let's try to do some observations. I take my interior of the isotropy of the self-similar groupoid, and I claim that they are the unions of those cylinder sets mu g nu, where so mu g dot x is equal to mu x for any x ending at source of source of mu. Equal, so I claim. So this equality is actually more or less direct forward. Well, first of all, so these things, once you satisfy the condition here, it is fully contained in the isotropy, and because themselves are open, so they will be contained in the interior of the isotropy. And if you, so this already proved that this part is included in this part. And if you look at the interior of the isotropy, well, because these cylinder sets form a basis, so for any open subset, you can always write them as a union. And what does these cylinder sets need to look like? Well, they need to satisfy this property, so that you can actually contain them in the isotropy. So this claim here is just a reasonable observation. Okay, so I will give those triples that satisfy this very nice property a name. They call the cycling triples. So some mu g nu is a cycling triple if this condition satisfied, or if and only if this cylinder sets is fully contained in the isotropy of the groupoid or the interior of the isotropy of the groupoid. And secondly, such a cycling triple will be called a symmetric cycling triple if mu is equal to mu. And thirdly, I'll take this as sim to be the subset of the interior of the isotropy, which is the union of all those cylinder sets coming from symmetric cycling triples. But for now, this SM is only a subset of the interior of the isotropy. Right. And the theorem that we're able to prove will give a complete understanding of these interior of the isotropy, at least under some mild conditions. So this be a pseudo-free, self-similar graph. And we need the additional condition that, so G has an element of infinite order. So in particular, we really wanted to cover the case of interest of G being Z. Then the interior of the isotropy will be the disjoint union of a sim. So the union of those cylinder sets coming from nice enough things with the union of cylinder sets alpha G beta, where source of beta is on a cycle with no entrance. So if you look at this equality and ponder a little bit a while, you'll realize that, well, this condition, the source of beta is on a cycle with no entrance, meaning that there's only one infinite path going into the source of beta. Right? And then according to how the cylinder sets are defined, although I write it as if it's really an open cylinder set, there's only a singleton contained in here. So what this interior of the isotropy is a nice enough subgroupoid, well, a subset. I haven't shown that any other property of it. So a subset, and you have singletons floating around. That's it. Okay, and what is more, so when G is additionally a billion, this sim is an abelian open normal subgroupoid of the interior of the electrode. Right. So really, the abelianness of the sim requires the abelianness of the group G, but the other properties you can show much more generally. And normality is the groupoid analog, or the kind of condition that you need to put on the groupoid so that the corresponding C-star subalgebra you get is regular, which is one of the properties that Philip mentioned. So the normalizer generate the bigger C-star algebra. Right, so this sim gives us a seemingly nice enough candidate for giving us a Cartan, but unfortunately, it is not always true that this sim gives you a Cartan, because the maximal abelianness is really the most tricky part. But we do identify some sufficient conditions under which this sim give you a Cartan subalgebra. So by invoking this paper of Anna Duenik, Gillespie, Norton, Resnikov, White in 2020, we have the following main theorem. So in this case, we'll just restrict ourselves to be the group B and Z, because as long as group becomes slightly more complicated, the computation is already out of control. So this be a pseudo-free, self-similar graph. So assume the following conditions. The first condition being, so for any infinite path and group element, X is either G generic or G rare. So as you might have noticed, this is exactly the same condition as what we had for the cross product. And it's really the categorization of closeness. And the second condition to ensure this maximal abelianness, so it's a condition on those cycles with no entrance. For any cycle C with no entrance, so if P is the smallest integer, so positive, such that a to the power of P, where A is the generator of Z, fixes C, then A to the P restricted cycle is not equal to A to the plus or minus P. So this is really try to guarantee the maximal abelianness of sim. Then the reduced groupoid C-star algebra of sim is a Cartan subalgebra. Right. So from my point of view, the real takeaway of this project is really not this theorem, but rather that theorem. So the actual point is that we get a complete understanding of the interior of the isotropy, And for the special cases or examples that people are interested in, they could try to conduct the computations. And for instance, this is a particular way that you can actually perform these computations. And it's probably worth mentioning that so even in the kind of easiest case where you have some C-star algebra generated by finitely many generators and relators, or just taking this to be said, we still don't really understand the existence of Cartan, because like in some of the cases where this G generic and G rare condition is not satisfied, then you don't really get a Cartan out of this picture, because the interior of the isotropy is the only choice. So in that case, even in this very simple case, we still don't really know how to find Cartans. And with that being said, I would probably like to conclude my talk.
You, Shanshan? Are there questions from the audience?
Thanks. No? Okay, great. So if you have a Cartan, you get like a different groupoid model, I guess, for the C-star algebra, right?
Yes.
But do you know how that looks like? So the twist, would that still be trivial?
You will get some like twisted groupoid model. But this is actually a very good question, because I think what you're thinking about is really this file groupoid construction. We do get a nicer groupoid model. In a sense, we get this like action groupoid, and you can indicate where like how the spectrum looks like, for instance. So the spectrum of the Cartan. And the spectrum actually looks extremely nice. So they are the disjoint union of solenoids, one solenoid corresponding to each infinite path. And you know that these solenoids are like these inverse direct limit of the torus, where the connecting maps are like so how many like circles around, basically, that's telling you the connecting map. That's basically determined by the restriction map like passing along this infinite path. So you can basically describe very explicitly about the spectrum of the Cartan that we obtained. Also, you can describe the action of the action groupoid, which is also the very natural thing that you would expect. But the only off part is really, well, first of all, you have a twist. And secondly, you might get a groupoid that is not necessarily Hausdorff.
Oh, like that groupoid you get from the Cartan? It's not?
So get from the Weil reconstruction is not necessarily Hausdorff.
Oh, okay.
Thank you.
Okay. And this twist, is it like a co-cycle twist? Can you describe or is it margin?
That I'm not completely sure, actually.
Mm-hmm.
Because I think even in our eventual paper, we probably only have a computation of how the action groupoid looks like, but not really that much onto the twist part.
Okay, thank you.
Yeah, no.
All right.
Cartan and the groupoid should be Hausdorff, no? Like this is like cum domino. These Cartans, I think, like whatever XL is considered, I think, but it's not the original like Renault stuff. I thought Cartan had to give you a Hausdorff groupoid.
All right. So I guess what you're thinking is really this, like the quingenre notes their correspondence, but maybe what I'm saying is slightly different. It's this file groupoid construction. I'm not sure that they're actually the same construction though. But
so it's probably like so yeah. So I was wondering, can you somehow get the groupoid you should get from the quingenre stuff by saying, oh look, it's a Cartan. Can you get that groupoid somehow more directly from the groupoid and the isotropy, I guess, that you started with, right? Like, can you somehow, I don't know, take some kind of weird quotient of the groupoid modulo its isotropy to get the new groupoid or something like this? I don't know, but
I thought probably you will need to start with some like open normal billion subgroupoid, and that would be fine. So I think what we are able to prove is that this asim, although it's not necessarily giving you a Cartan, it will always satisfy the property that you can feed into these kind of like new groupoid construction. So like even just looking at sim would already allow you to recover different groupoid. You don't actually need the Cartan construction in full force. Mm.
Also, I think the battery is so the graphs and those are controls numbers, right? And also, I think maybe it's kind of. I think they're both a little bit. Thank you. Okay, so I just repeat. So graph algebras are constraintional algebras, right? And I think also these Nekrashevich algebras from the self-similar groups are constraintional algebras. So are these guys also, at least if the groups are the integers, because otherwise maybe one would rather get like a product system of the group. Not sure.
So you mean what needs to be integer?
Or like if the group, like you have this pair GE, right?
Oh yes.
I would expect that if the group is the integers,
Uh-huh.
then perhaps you get a constraintional algebra.
Yeah, maybe. I don't know. I don't know that much about constraints or algebras in two.
Okay, I was just curious.
But at least for Kirchberg algebras, they do admit like these Kunstpimster algebra construction, right? Or then yeah, very likely. Yeah. Well, for graph C-star algebra, I kind of see how you do this C-star correspondence, but I'm not so it's not so clear for me how to do it for the self-similar graph C-star algebras, even when the group B and Z, let's say. Yes.
Diagonal? CSR diagonal?
So they're only diagonal probably in very special cases. So in general, they wouldn't be diagonals.
Sorry, they are not diagonal.
They're not.
But do you know the conditions that they are diagonal?
I think we didn't spend much time on that, but it shouldn't be that hard because I think Anna probably in her recent work has some criteria on the level of groupoid that you can actually see whether the groupoid give you a diagonal or not. Mm-hmm.
Because then maybe there's also some notions of the diagonal dimension.
Right. So
diagonal dimension.
I think that will probably be a little bit overkill because so there are these notions of diagonal dimension and Cartan dimension. If you're a Cartan but not a diagonal kind of diagonal dimension blows up to infinity, then probably that's what you mean.
There's a work of the Wilhelm.
Yes. Yeah, that's yeah. But I think like probably you could just do this with much easier. Like you can probably just try to do this file groupoid reconstruction and then look at this twisted groupoid that you obtained. If it has some nice properties like principal, then yeah. That diagonal dimension, although it's defined, but I don't think it's that easy to compute. That's my impression. Yeah, sure.
Maybe one more quick question. Have you tried generalizing the main theorem to Z to the D actions?
Well, there might be a problem because like so at least part of our argument actually relies on this condition. So you have an element of infinite order.
Yeah, so it's like D copies of Z.
Take some. Yeah, I mean, it probably involves more explicit computations, but based on this framework, you can probably do that.
Or at least, yeah, use similar techniques to, because I mean, none of your current statements on the board, aside from the last one, require the group specifically to be just said.
Like you can probably expect that you will need to change very much this condition here. Like, so this condition is very much like just designed for the group being Z.
Yeah,
if you have Z to the D, then you will have something completely different.
Yeah. Yeah.
The group or a discrete combo, yes.
Okay.
Because all you need to do is basically just picking out, like to see whether these floating singletons are actually commuting with sim or not. So it's just merely computation.
Right. Any questions from the online audience? If not, then let us thank Shanshan again. We will be back next week. Talk by Fabio Gavarini.